So we've explained oxidation as the reaction of an element with oxygen, or you could say the gain of oxygen, reaction with O2. And we've seen that when something reacts with oxygen, what typically happens is oxygen steals their electrons. And so oxidation can also be defined as the loss of electrons. Why does oxygen steal electrons? Because it's very electron hungry. There's oxygen over there. All it needs is 2 more electrons in its outer shell in order to become a noble gas-like thing, in order to attain a full outer shell. And so it's going to be really electron hungry, and it steals electrons from things that it reacts with. So when you react with oxygen, you best be sure that you're going to lose electrons. And so those are 2 definitions of oxidation. There's a last definition of oxidation which concerns the movements of hydrogen. And this one is a bit more relevant in organic chemistry. It's more relevant in organic chemistry. And I'll see if I can try to explain why. Let's consider a chemical reaction. Let's take hydrogen sulfide reacting with oxygen. Now this reaction is something that is done actually by certain bacteria. Certain bacteria take hydrogen sulfide, react it with oxygen, and they use that to get energy for their metabolic processes. So H2S plus O2 gives you, one of the possible sets of products is sulfur plus H2O. Sulfur plus H2O. And this, as you can imagine, is an oxidation reaction because we've reacted hydrogen sulfide with oxygen. It's an oxidation in another sense, in the sense of the movement of hydrogen. And let me show you that. So sulfur is in group 6 on the periodic table. Oxygen is in group 6. Hydrogen is in group 1. So if we draw their outer shell electrons, sulfur has 1, 2, 3, 4, 5, 6. And when it binds with hydrogen as a covalent bond, we're going to have basically this set of electron gets shed, and that set gets shed. So those 2 are shared, those 2 are shared. And now hydrogen has 2 electrons, so its outer shell is full. Sulfur has basically 8 electrons, so its outer shell is full. Let me show you that quickly on the periodic table. When hydrogen gains 2, it now looks like neon, and so it's full. And when sulfur gains 2, it then looks like argon, and so it's full. Now we proceed. So if this reacts with oxygen, what's going to happen? Here's oxygen. And I'm going to draw a single oxygen atom. But remember that oxygen was like that. Okay, 1, 2, 3, 4. 1, 2, 3, 4. And each of these bonds is 2 electrons. And so we got 6 from this guy and 6 from that guy. But they can split up into just 1 oxygen molecule. Okay. Oxygen is electron hungry, as we already know. It doesn't like to be in this 6 state. So it looks over at sulfur, and in theory it could steal this set of electrons over there. But it performs a different trick. What it does is it looks at hydrogen over here, these 2 hydrogens, or these 2 hydrogens. And hydrogen is not very good at hanging on to its electron. Hydrogen is fairly puny. Hydrogen is fairly small and tiny compared to the big boys of organic chemistry. Who are the big boys of organic chemistry? Carbon, nitrogen, oxygen, phosphorus, I guess as well, and sulfur. These are the big boys of organic chemistry, and they're pretty electron hungry. They really want to go that way in order to become like the noble gas. Hydrogen, on the other hand, is not as electron hungry. It's not as electronegative. So when any of these organic chemistry bad boys reacts with the hydrogen, it ends up bullying the hydrogen. So when chlorine, or when fluorine, for example, I guess fluorine isn't organic chemistry bad boy. Let's use nitrogen. When nitrogen reacts with hydrogen, you have 5 outer shell electrons for nitrogen, right? And it's going to share 3. So we're going to have 1 hydrogen here, maybe sharing there. and then one hydrogen there may be sharing there, and then another hydrogen there may be sharing there. But these sharing bonds are not equal at all. So these sharing bonds are very partial to the nitrogen. So nitrogen basically is bullying hydrogen of these electrons, and nitrogen is hogging the electrons. Nitrogen is hogging the electrons. And so hydrogen is not very good at holding on to its electron. And so in any covalent bond with hydrogen, most of the electron density is closer to the nitrogen, or to the oxygen, or to the carbon, or to the phosphorus, or the sulfur. Okay? And therefore, now, if we go back to this reaction, this covalent bond is actually a bit more partial. It's a bit more partial to the sulfur. Sulfur is hogging those electrons. So if oxygen manages to steal hydrogen together with its electron, if oxygen manages to steal hydrogen with its electron, now oxygen has basically gained an electron. Okay, let's flip that over. Oxygen has basically gained an electron. How has oxygen basically gained an electron? Oh, these electrons are getting all messed up. Because hydrogen is puny and small and can easily be bullied, most of the electron density is concentrated around the oxygen. Okay? So you could say that oxygen now has 1, 2, 3, 4, 5, 6, 7, 8 full shell. Hydrogen is kind of happy because it's kind of sharing with oxygen, but not quite. And that's what happens in this reaction. So let's draw it again. Let's try and make it a bit cleaner. This is very, very ugly. Let's try and make it a bit cleaner. So we have sulfur, which is bonded to a hydrogen. It has 6 outer shell electrons, 2 of which are being shared with this hydrogen. Okay. Oxygen is going to come along with its 6 electrons and say, hey, you there, I want your hydrogen. Why? Because I want to bully that hydrogen of its electron and hog that electron. So then oxygen, let's move this oxygen over there. The oxygen that's going to become water now is going to take this guy, okay, and bond with him there, okay. And he's going to take, of course, this guy as well and bond with him at the other side. And remember, this is not a fair bond. This is an unfair bond. And we're left on the other side of the equation with sulfur on its own. Sulfur has been oxidized. It has lost those hydrogens that it used to bully for electrons. So it has lost hydrogens, all right? So oxidation, we defined already as the loss of electrons. And you can see that when you steal someone's electrons, then you also, when you steal someone's hydrogens, you also make them lose electrons. So another way to make something lose electrons is to take its hydrogen. So oxidation can also be defined as the loss of hydrogen. And this definition, loss of hydrogen, I'll put a quick asterisk on it because it's not always the case. You'll see that in certain cases, especially with reactions with other metals, the loss of hydrogen does not necessarily mean an oxidation. But for most of the reactions you look at, especially in organic chemistry, especially in orgo, oxidation is indeed the loss of a hydrogen.